Hello, my name is Michael Warren-Angelucci. Today I will be talking about my senior project, the Strider manufacturing process. Imagine not being able to use your legs to support yourself. How would your life be different than it is now? Diseases such as Parkinson's and muscular dystrophy cause defects in muscle proteins, limiting a person's ability to stand on their own as well as their ability to walk. The goal of the Strider project is to create a mobility device that can support a person with weakened leg strength and enable them to maintain a standing position. This picture here shows the prototype of the Strider in use. Before manufacturing the product, it will be very important to create the design of both the product and the manufacturing process. A group of mechanical engineers from Cal Poly have created a prototype of the Strider, and it will be important to decide whether the design is the best and what improvements can be made on it. Once this is established, it will be important to design an ergonomic and cost-effective manufacturing process for the Strider. This design will be based on research and different criteria. There were many things needed to be done before creating the manufacturing process. After verifying the design, the next step was to create a bill of materials. This helped me determine the different sub-assemblies and which parts went into each. It also enabled me to document the part cost, the shipping cost, and the lead time for each part, which was needed to determine the total cost for each product. The next step was to get price quotes for each of the manufactured parts. This let me complete the bill of materials. Before creating the manufacturing process, it was also very important to determine a forecasted demand. This is because I must know how many of each part was needed for the process and when they would be arriving. The final step was to create the manufacturing process. Prior to me joining the Strider team, some work was already accomplished. A team of mechanical engineers had put together a design for the Strider. Their design incorporated what the customer wanted while being structurally sound and safe. Below is the design that they came up with, including the top assembly and all the parts. The first step was to verify that the previous design of the Strider was manufacturable and fit the customer's needs. One of the requirements of the Strider is that it was easy to assemble and use in the customer's hands. The customer must be able to open the box of the new Strider and be able to assemble the device with ease and need no tools. They must also be able to disassemble the product where the separate parts can fit into their car or storage closet. This is achieved with locking pins. Locking pins enable the customer with one hand to easily take apart the Strider at its joints. The locking pins are connected to the inserts, and the inserts are used to join different assemblies together. Shown here, you can see where the locking pins were located in the previous design. As you can see, the locking pins enable the customer to separate the front and back assembly from their corresponding carbon fiber connectors. However, in this design, there are no locking pins located between the back wheel assembly and the portion of the Strider that supports the hanging customer, leaving the customer with one large piece that is non-detachable. This promoted a change in the previous design to incorporate locking pins and inserts between the back wheel assembly and the vertical hanger assembly. In order to accomplish this, small design changes were made to the tri-joint and the angle joint. Previously, the carbon fiber rods were glued directly to the tri-joint and angle joint. However, with a new design, carbon fiber is glued to an insert which connects each joint using quick release pins. It was very important to make a detailed bill of materials for the Strider. The team of mechanical engineers had a very vague parts list, and from the manufacturing view, the BOM must be very thorough and kept up to date. The BOM has 3 levels including the top assembly. It contains each assembly and shows which parts are in each assembly, as well as important details for each part. As you can see here, this is the bill of materials for the Strider. Once the design was complete, the next step was getting press quotes for all of the parts. The part models for the major parts were sent to 2 different companies, Tuteman Ltd and R&D Manufacturing. Tuteman LD is located in Shenzhen and was chosen because my brother is the project manager for the company. Being a very reliable company, he was able to get me accurate quotes in a timely manner. R&D Manufacturing, located in Santa Barbara, was chosen because they are also a very reliable company that does outstanding work. Because I've worked with them before, the manager was eager to give me price quotes for all of the parts. As you can see here, all of the price quotes are arranged in tables from each of the companies. Before choosing between the price estimates from China and Santa Barbara, it was important to see whether it would be more cost efficient to create the parts in-house. Creating the parts in-house would be more environmentally friendly as there is not a constant need to ship the parts. However, creating the parts in-house would create more time for each assembly as the worker would need to do additional work such as cutting, milling, and welding. For many of the parts, a cost estimate for making the parts in-house would be very difficult and possibly inaccurate. This is because many of the parts are complex, as some of them need to be milled, welded, and heat treated. Because the Strider project does not have the current funding to create all of these parts a second time, it would be impossible to create a cost estimate. Because of all the reasons mentioned above, it was determined that an in-house cost estimate would be able to be done for the carbon fiber tubes, as they are relatively easy to make. In order to make the carbon fiber tubes, the raw material must be bought, the tubes must be measured, and then cut. In order to accomplish this, only 3 items must be bought: the tubes, a measuring tape, and a bandsaw. As you can see above, the cost of the bandsaw or measuring tape was not incorporated into the final cost estimate. This is because the cost is negligible when making 10,000 products or cutting 70,000 carbon fiber tubes. For this project, it was decided that 10,000 products are going to be made over 10 years. After receiving all of the cost estimates, it was determined that the carbon fiber tubes would be manufactured in-house. The hanger, angle joint, and insert would be outsourced to R&D manufacturing, and the tri-joint, extender, and one-sided fork will be outsourced to 2-Min Ltd. The next part of the project is the assessment of the forecasted demand for the Strider. Because the Strider is a new product, its demand forecast cannot be compared to previous year or quarter's demand. Determined previously, there are roughly 10 million people in 300 recovery clinics that are potential customers in the United States. Because the Strider will not be an inexpensive item, I will assume that approximately 1,000 of the population will purchase a Strider, and all of the recovery clinics will buy one as well. From these numbers, the Strider will have an estimate of 10,000 customers over its life cycle. It was very difficult trying to determine a range for how long the Strider could potentially be on the market for. I assumed that the Strider would stay on the market for 8 years for 2 different reasons. The first being that because it's a medical device, it may become outdated relatively quick, and someone may come up with a device that produces better results. The second being that it will take a while for people to recognize that the product works. This led me to believe that it will not have too short or too long of a lifespan. The Strider should follow an average product life cycle. Its demand should flow in 4 different stages: introduction, growth, maturity, and decline. To replicate this, the product demand should also follow the same pattern. Because the product lifespan will be estimated at 8 years, the percent of total demand will be broken up into 4 different stages, each 2 years long. The percent of total demand will be as follows: 15% for the first 2 years, 50% for years 3 to 4, 30% for years 5 through 6, and 5% for the last 2 years. Only the forecast demand for year 1, month 1 and 2, and year 3, month 1 were done for a couple of reasons. Year 1 forecast was chosen to get a feeling for how the ordering process would commence. Year 1 enables the manufacturer to see trends and understand the flow of the ordering process. Year 3 was chosen because it's the start of the growth stage. During year 3, the Strider will be at its greatest demand, and the manufacturing process must be able to withstand this demand. Other years and months forecasted demand were not done because they are in between year 1 and 3. As long as the manufacturing process can handle both year 1 and 3, then it will be able to handle the rest of the year's demands. After determining the forecast plan and how many items are going to be needed for manufacturing at what designated times, the next step was to analyze the manufacturing process. In order to do this, I designed a simulation of the assembly process using ProModel. The design manufacturing process for the Strider contains 6 locations: an inventory stage for both raw materials and partially assembled parts, a glue station to glue the carbon fiber to the aluminum joints, a dry station for drying the freshly glued objects, a cut station for measuring and cutting the carbon fiber into the desired lengths, and an assemble station for assembling the front and back wheel assemblies. Each step in the manufacturing process had wait times associated with it, which corresponded to the length of time in order to complete each step. Again, because of the funding issues, it was impossible to recreate the Strider, which meant that it was also impossible to know how long it would take for each of the above-mentioned steps to take. Also, in order to have a more accurate time for each step, many Striders must be made, and the time for each step must be recorded and averaged. This forced the time for each step to be made up, however, using reasonable assumptions. In fact, each time was over-exaggerated in order to not underestimate the manufacturing process time. Shown here is the simulation for year 3, week 1. Using the information determined from the demand forecast, I was able to determine how many parts were needed to create enough Striders for the demand in week 1. This process would run as a pull system or Kanban system, so that each sub-assembly would be created as the order came in. This is because the Strider is an expensive product and will be manufactured as needed rather than being pushed out into the market. In this simulation, all the parts arrive at the first inventory station at the beginning of each week. Each part would then travel to its necessary location, and the desired action would be completed. After each subassembly is created, they would then travel to the second inventory location. Once all the subassemblies have made it to the second inventory location, they are then boxed and ready for shipping. From the simulation, I was able to determine that for year 1, week 1, that the maximum inventory at inventory station 1 was 1,008, and at station 2 it was 80. The percent utilization, or the percentage that each station was used, was 20.51% for gluing, 1% for drying, 19% for cutting, and 30% for assembling. For year 3, week 1, when the demand is 53, the maximum inventory was 3,339 at station A, and at station B the maximum inventory was 265. The percent utilization for gluing was 68%, for drying it was 3.4%, for cutting it was 63%, and for assembling it was 99%. So as you can see here, the assembly station is the bottleneck. I was able to determine that each product is approximately finished in 1.68 hours. At peak demand, in order to accomplish the 53 items per week goal, the factory must be working at 13 hours a day at 7 days a week. This is only for the scenario if one person was doing all the work. If the demand ever reached more than 53, the only solution would be to have another assembly station as to minimize the bottleneck, or to have more than one worker. The final part of the project is to determine the total cost per each product. In order to do this, there are multiple factors that go into the total cost. The first is the labor expense per unit. The second is the inventory cost per unit. The third is the part price per unit. And the last is the shipping price per unit. In order to determine the labor expense per unit, I have first determined the amount of time per unit, and then I assumed that we would be paying our employees $15 per hour. The total price would come out to $25 per unit. In order to determine the inventory cost per unit, I assumed that each unit of inventory per week would cost 50 cents. From the simulation, I was able to determine that the maximum inventory was 3,604 units, so the total came out to $34. The bill of materials extremely helped me to create both the part price per unit and the shipping price per unit. For the part price per unit, the top assembly came out to $333, the front wheel assembly came out to $72, the hanger assembly came out to $185, the 30-inch carbon fiber tube assembly came out to $220, the 30-inch carbon fiber tube assembly came out to $263, the back wheel assembly came out to $65. So the total part price per unit was $1,142. For the shipping price per unit, for the top assembly was $18, the front wheel assembly was $25, the hanger assembly was $15, the 37-inch carbon fiber tube assembly was $22, the 30-inch carbon fiber tube assembly was $28, the back wheel assembly was $16, so the total shipping price per unit came out to $127 per unit. So in order to determine the total cost per unit, I added up the labor expense per unit, the inventory cost per unit, the part price per unit, and the shipping cost per unit. I also added a miscellaneous expense which included electricity, paying for the building, and other miscellaneous expenses. The total cost per unit came out to $1,376. Thank you for watching this video. I hope you enjoyed it.